Hi, my name is Rasmus. I'm presenting the package Bender.jl, which is a utility package for customizable deep learning. Feel free to check out the GitHub repository and the documentation for more information. Deep learning frameworks typically provide some standard layers. Neural activations are determined by a forward pass, typically matrix multiplication or convolution, followed by a nonlinearity. Changing the nonlinearity is easy. However, changing other aspects of the mapping requires writing custom layers. The goal of this package is to make it easy to customize every aspect of the forward and the backwards pass. And in the following slides, we'll see some examples of how this can be done. This package aims to be compatible with Flux and to have similar API. It comes with two new layers, generalized dense and generalized con. Each layer takes additional keyword arguments, which allows instantiating additional trainable parameters. This is useful for certain experiments. When not supplied, these fields will default to false. The optional keyword forward allows users to supply a custom forward pass, or use one of the forward passes shipped with the package. As an example, here we'll see how you can create a fully connected radial basis function layer. The function radial here just computes the negative squared Euclidean distance between rows of the weight matrix and columns of the input data. Let's have a look at a couple more examples. First, we consider binary neural network training. In this setting, weights and/or activations are restricted to be either -1 or +1. The binarized weights are obtained by applying the sign function to a set of real-valued weights. However, this is a bit problematic as training requires backpropagating through the sign function. And the derivative of the sign function is 0 everywhere except at the origin where it's undefined, so regular backprop is going to fail. A common approach is to use a differentiable surrogate during the backwards pass. Common choices include tanh, hard tanh, and the identity function. In the following, we will use identity. In order to train the binary neural network, we need to define a function signSte, which acts like the sign function in the forward pass and acts like the identity function during backpropagation. The ChainRules call library makes this very easy to achieve. We then define a forward pass, which applies our signSte function to the weights. Note that this function, as well as signSte, also ships with Bender, so you wouldn't have to write this in practice. And finally, we instantiate a trainable binary layer using signSte as the neuron activation function and by supplying the custom forward pass we just wrote. As a final example, we will have a look at the biologically motivated learning algorithm feedback alignment, which addresses the biological implausibility of weight symmetry. Backpropagation requires that the same weights are used for making predictions as are used for transporting errors during the backwards pass. This symmetry is considered biologically implausible, as in biological neural networks, signals only flow through axons in one direction. This means an entirely new pathway is needed in order for the orange neuron shown here to receive a feedback signal from the blue neuron. In the following, we will see an example of how feedback alignment can be implemented using Bender. Feedback alignment is a simple algorithm which shows that weight symmetry is not strictly required for learning. In the forward pass, nothing is modified. However, in the backwards pass, we'll use fixed randomly initialized weights to transport errors. Graphically, this can be shown like this. In the forward pass, neuron activations are computed via a linear transformation followed by an activation function f. In the backwards pass, the partial derivative dA dx is modified to be computed using a fixed random matrix instead of the transpose of W. This is straightforward to implement using ChainRules core by defining a custom R rule for the linear transformation. Now let's have a look at how this can be implemented using Bender. First, we define a custom matrix multiplication function along with the corresponding ChainRules core R rule. The R rule computes the partial derivative with respect to x using the fixed random matrix B rather than the analytically correct choice W transposed. For brevity, the R rule is not included on this slide, but it can be found in the package repository. Next, we define a forward pass, which uses our custom matrix multiplication function. And now initialize a dense layer, which can learn without weight symmetry. A convolutional variant can be created in a similar manner, using functions shipped with Bender. So, in conclusion, Bender.jl is a small utility package which makes it easy to experiment with a wide range of atypical neural network architectures without having to spend time on boilerplate code. The API aims to match Flux, which makes it easy to integrate into existing workflows. For more information, check out the repository and the documentation.